Hello, I'm John. This is joint work with Nicolas Rivera and Thomas Sauerwald. Most of this work was done while Nicolas and I were postdocs of Thomas at Cambridge. Nicolas is now in Chile, the Millennium Institute, and I'm now here in Glasgow as a postdoc of Kitty Meeks. So, a random walk is a Markov chain, and it's a very simple one where an undirected, unweighted graph in our case, and at each step, our walk is at a vertex, and it moves to a uniformly selected neighbor in each time step. So it looks something like this, and we assume that at each step, it stays at its current position with probability half. And this is for technical reasons that I'll explain later, although when I draw an animation, I don't include the lazy steps. So what are we interested in? Well, mostly we're interested in the cover time. So this is the first time which every vertex of the graph has been visited by our walk. So if we have a little example here, our walk starts at vertex A, goes to B, C, D, or E, back to C. So it's just each step uniformly choosing a neighbor to go to, and we stop the walk when it's visited every vertex of the graph. So this is very well studied for single random walks, but we're interested in what happens when you have more than one random walk at the same time. And this is the setting of multiple random walks. So you have k independent walks, so copies of the same Markov chain, all running synchronously at the same time on the same space or graph. And we're interested in the cover time, which is the first time that every vertex has been visited by at least one of the walks. Okay, so here's another example. We've this time got two walks. They both start A, and they go their separate ways. So they're moving independently, each going to a uniformly selected neighbor each time. So now they're going to swap vertices, and then the green walker is going to go to F, and that covers the graph. So what we're interested in is the expected amount of time to cover the graph, so visit every vertex, when we condition on starting all walks from the same worst case start vertex. And we call this the worst case cover time. Okay, so this is going to be one of the things we study. So single walks have found many applications over the years. And so in our opinion, it's only natural that you ask how well do random walks parallelize? Okay, so this question was actually asked first by Alon et al. In 2008, and they introduced this quantity, which is the speed up. So it's the cover time of a single walk divided by the cover time of k walks, both on the same graph. So it's some function of k in the graph. So how big is the speed up? Well, you might think it's actually just linear all the time. So provided k is not too large, so the number of walks is not too great, you do actually have a linear speed up on expanders. However, for the cycle, it's a different story. And, and actually the speed up is logarithmic in k. Okay, so you see there's something a bit more interesting going on here. And actually for the binary tree, you get this interesting kind of square root k growth of the speed up. And for the 3D grid, and you can have kind of two behaviors. So if you're up to n third, then you get linear speed up. And above that, you get this kind of logarithmic speed up like you have in the cycle. So there's some, there's a few factors at play here which influence the speed up. It's not a trivial question. So for most basic networks, i.e. your favorite graphs that have names, like the ones above and others, this is known, this speed up. And then the general conjecture is that this speed up k is between log n and linear. So that means that the expander and cycle are the best and worst cases, respectively. This is actually still open. There are some upper bounds by Flamenco and Rheingold. I don't think there's any lower bounds, but it's still open. And a more general question is, can you characterize the speed up in terms of graph properties or random walk quantities? So what makes the binary tree square root speed up, for example, and the cycle so bad? So this is more this last point is more the direction we want to take in this work. Okay, so one random walk quantity you can consider is how fast a single walk converges to its stationary distribution. So every random walk on a connected graph has a unique stationary distribution, and we assumed our walk is lazy, so stays put with probability half. So you know that it will converge to the stationary distribution. So I've got a little example of this. We start on this red vertex here, and the value of a vertex is going to be the probability that you're at that vertex at time t. And if we just run this walk, you can see that the probabilities kind of level out. And that's because the stationary distribution is uniform on a cycle, and we're converging to this uniform stationary distribution. So how long a walk takes to converge to its stationary distribution is a key quantity for single random walks, and it's known as the mixing time. But there can be many different notions of mixing time depending on how close you want to be to the stationary distribution and how do you measure close. So I'm going to give you a few notions of this on the next slide for single random walks. Okay, so the first one, we say that a randomized stopping time. So think of it like a randomized algorithm that runs for some random amount of time and then stops. So a randomized stopping time is a strong stationary time if the probability that once a randomized stopping time fires, if you run a random walk from any start vertex for that amount of time, then the distribution of the position of that walk is going to be exactly the stationary distribution, and that's independent of the time that the stopping rule fires. So that's a very strong notion of stopping time, and you might say that the mixing time is the expectation of this random variable. For example, that could be one notion of mixing time. And we see there, once this random time has occurred, then you've actually got perfectly the stationary distribution. So it's quite a strong notion of mixing, in my opinion, this one. So that's a very qualitative notion. A more quantitative notion could be the total variation mixing time. So this is just, you look at your empirical distribution of the walk, so where it is after t steps, what's the probability of being at any vertex, and you take the L1 norm with that distribution and the stationary distribution, and you ask for the minimum amount of time t such that distance is less than a quarter. So this is the L1 distance. Okay, and about a decade ago, Perez and Soucy, and independently Rivera, showed that this L1 mixing time is the same up to constant as the expected time it takes for a random walk to hit any set, like a worst case set of size stationary probability a quarter. So you have some set which is roughly a quarter-ish of the size of your graph, and you're trying to hit it. The amount of time it takes to hit this set is up to constants, the same as your 1/4 total variation mixing time. Okay, so that connects the bottom two quantities, but actually there's an old result by Diaconis and Aldous that says that there always exists a strong stationary time whose expectation is up to constants bounded by the mixing time, the L1 mixing time in the middle. So actually kind of all three of these things are intimately connected. And there are many other notions of mixing for single walks, but these are ones which we shall focus on. Okay, so what we're going to do is we want to try and characterize the worst case cover time by multiple random walks in terms of some quantities. Our candidate for this is going to be some new notions of mixing that we come up with specifically for multiple random walks. And we're going to look at the the cover time by k walks, not from worst case, but from stationary. So this is going to be our new notion of mixing. So we're going to call this the partial mixing time of k walks, k tilde walks out of k. And so this is the smallest time t such that there exists a strong stopping time, so that the probability that this stopping time is fired by time t is at least k tilde over k, and it doesn't matter where you start the this from. So this is how we're going to relate kind of mixing time of single walks with multiple walks, because this strong stopping time is a strong stopping time for a single walk, and this quantity is the probability that you have a single walk and the stopping time fires before time t. And so we say that this mixing time of k tilde out of k walks is the smallest time t, such that this probability your single walk has stopped is at least k tilde over k. And one way to think about this is if you start k walks walking independently on a graph, this is the amount of time you need to wait, such that if you wait this amount of time, in expectation, k tilde of your walks will be mixed. Okay, and then we discussed cover time from worst case. Well, this is cover time from stationary. So you start k independent walks, all of them from an independent stationary vertex. Okay, and trust me for the time being, but this is an awful lot easier to deal with than cover time from worst case. We'll discuss this in a bit. So what's our bound? So our bound is that the worst case cover time is at most, and it's a min-max. So you're allowed to choose any k tilde, and you say that the worst case cover time is at most the maximum out of the time it takes to mix k tilde out of k walks and the time it takes to cover your graph from stationary using k tilde walks. Okay, so how does this work? Well, it's quite simple actually. So you run your walks for amount of time which is some constant times the mixing time of k tilde out of k. And so after this amount of time, with constant probability, you can actually find k tilde walks which have mixed. So then you take these k tilde walks, you just focus on them, ignore everything else, and you wait an amount of time which is a constant times the expected amount of time for k tilde walks from stationary start to cover the graph. So with some constant probability, they will be successful and your graph will be covered after this second phase. And if not, well, you rinse and repeat. So you then mix again, find your walks and try and cover. So so in expectation, this thing takes constant times the max of the two, and you're free to choose your k tilde. So this is our upper bound. It looks simple. It is quite simple, but it is actually tight for many graphs, which we'll see for later on. Okay, and we also have some lower bounds. So unfortunately, we need to introduce a second type of mixing of k tilde out of k walks here. And this one, the last one was based on strong stationary times. This one is going to be based on hitting times of large sets. So we say that k tilde out of k walks have mixed. So this is the minute you take, this time is defined to be the minimum t, such that if you're trying to hit any worst case set, which is sufficiently large, the probability that a single walk has hit this set in time before t is at least k tilde over k. And similarly to the last quantity, this is, if you wait this amount of time is, if you run a random walk, if you run k independent random walks for this amount of time, then you would expect that k tilde of them have hit any fixed set of stationary probability greater than a quarter. Okay, from any start vertex. So we have some lower bounds here in terms of this quantity. We conjecture actually that this is the same up to constants as the other notion of mixing time. I think we're working on a proof of that, but if this actually had the partial, sorry, if this had the this mixing time, and our conjecture was true, and you had the cover time from stationary of k walks here, k tilde walks here, then this would be a complete characterization. Unfortunately, you don't quite have that. We have these other quantities, and where do these come from? Okay, so again, you start your walks from the same place, and you run it for an amount of time, which is like the time to mix k tilde out of k. So after that amount of time, with some constant probability, at most k tilde of your k walks have actually hit this hard to hit set S. And you know that for the graph to be covered, everything in S has got to be visited. And so from there, you focus on these k tilde walks, and you don't know when they arrived at S. So you actually just assume they arrived at time 0. And you ask, how long did it take for these k tilde walks between them to visit everything in S? Well, you assume they cover everything efficiently, and you can get a bound on the amount of time that must take based on the size of S. So it's quite crude, this lower bound, I'm not going to lie, but between these two bounds, they're actually tight for many graphs, which is quite surprising if you look at them. And I think the reason is that really this cover time is actually largely determined by the partial mixing times when you have large enough k. So that's our lower bounds. So we have upper and lower bounds. As I say, it's not a complete characterization, but for many classes of graphs, it's actually the upper and lower bounds match. Okay, so these upper bounds involved stationary cover times. So this is where you have k walks, and you start them all from independent stationary, and you ask how long does it take to cover the graph. So it'd be very useful if we had some bounds on stationary cover times. And as I said, these are easier to deal with generally than worst case cover times. So what's known? So this is a nice bound, quite old now, by Broder, Carlin, et al. And they give this upper bound that holds for any graph. We actually refine this a little bit, we'll improve it. We can shave off a log n, and we can slide in a d min on the bottom. So for some graphs, this is actually a significant improvement. And our bound is tight for the cycle with large K. I should mention some other recent work. So this actually appeared after a year after we finished this work. This is very recent, only a few months old. Herman and Susi have shown that for any K, the cover time from stationary of K walks is bounded by the cover time for a single walk divided by K. So this is very nice. This actually says that the stationary speed up, so the speed up of K walks from stationary, is actually always at least K, which is very different to the worst case. Okay, so I should mention that in the iCalc version of this paper, this work I'm discussing here, we proved a weaker version of this bound. It's just a half page proof where we had t hit log n here instead of cover time, and they've actually got the tight proper result, which is t cov divided by k. But this is a serious work. This is 20 odd pages just to get this one bound, and ours was half a page to get the weak bound. So I don't feel too bad about that. Okay, what about lower bounds? So this is a classical result from Aldous. It's kind of a coupon collecting bound, holds for any graph, and it says that from stationary, the cover time is at least constant times n log n. So we show that actually this analog of this holds for any k, which is not too large. And for k above small constant times n log n, there's actually some probability that you just, if the graph is regular, you've got a walk at every vertex. So this is kind of a natural restriction. And this gives a lower bound you'd expect. Okay, so very quickly, how do we prove this? Well, it's actually via a coupling with the oldest result. So the oldest result actually holds in slightly more generality than this. It also holds for weighted graphs. And we take a special graph where you've got an extra vertex, and you cook the weights such that you can break a single walk's trajectory into sections, enough sections where it walks on the graph for a bit, and then it'll go to Z. And whenever you go to Z, by the way that we've cooked up the weights, your next step moves to one of the original vertices of the graph with a probability which is proportional to its stationary distribution. So that's it, and you can build a coupling from that. There's all the details obviously on the archive. I haven't got time to go into it. So that's our result. Okay, so let me try and summarize what we can do. So we were trying to control and characterize worst case cover times in terms of the properties of the graph and number of walks. So we came up with some new bounds that bound worst case cover times in terms of this new notions of mixing and stationary cover times. And so what we did was we actually determined stationary cover times for many classical graphs to try out our new bounds, and then we used them to recover the worst case cover times, which is in this column here. Now I should mention that anything in green is new, so a new result of this paper, and things in grey are bounds where we've recovered a known bound for worst case start vertices for k walks, and reproved it using our new methodology. So the only case which didn't quite work is for the two-dimensional tori. Our new methodology gives the upper bound very cleanly. The lower bound, it's not easy to get it with our methods. But that's the one case that we found, and everything else works quite nicely and cleanly. And actually for binary tree, this worst case wasn't known. And also we can treat slightly more broad range of graphs with decent expansion than was previously studied in the literature, including preferential attachment graphs. Yeah. So yeah, so this was just kind of an application of some of our bounds. We have other bounds that were not mentioned in this talk, and our new methods with these max-min bounds. Okay, so have we answered the question? Well, I would argue that we've improved the state of knowledge regarding how do you characterize the speed up in terms of graph properties or random walk quantities. And we did this by introducing these new notions of partial mixing. Okay, so you should always end a talk with some open problems and conjectures. So this is a very appealing one to me. Throughout this talk, I assume that all walks start from the same vertex when we consider the worst case. But actually, you can start them all from different vertices, and the conjecture is that these two are the same. So I think Efremenko and Reingold conjectured this, and many works just implicitly kind of assume this conjecture, but it's not actually proved anywhere. So I've had a go at this, and it's not as easy as it looks for some reason, or I just haven't found the right technique. But I think this is a very nice conjecture. And this conjecture actually would imply a kind of another result. So we proved this bound, this constant times n over k log n bound, lower bound, for when all of the walks start from stationary. And that, of course, is a bound for when the walks start from worst case. So worst case, different start vertices. But we conjecture this also holds when they start from the same vertex. So we've actually proven that this side is greater than constant times n log n over k. We conjecture it also holds with the side. So of course, this first conjecture implies the second. But it might be possible to prove this independently. Okay, thank you very much.